you've just read a homework or quiz or test problem, and it talks about a heat exchanger. And generally, there's going to be two streams of substances involved in this problem. So, gosh, what's a heat exchanger? Man, the textbook does not really talk about heat exchangers, but I'm supposed to know about it. Let me try to give you some tips. One, about what is a heat exchanger, and also how would you start with a sketch? How would you come up with some reasonable looking sketch to start solving your heat exchanger problem? So here we go. And this is a video where I have not been able to copy and paste those repetitive steady state, steady flow, one inlet, one outlet uh, governing equations. And you're going to see why in just a second. So here are some examples of different heat exchangers. Let's see, let me go. Well, first, I've circled this one in red because this is the most basic way to communicate a piece of equipment called a heat exchanger. Basically, no matter what it is, this sketch is a way to communicate a heat exchanger situation. Now, a little over to the far left, here we go. This is an actual image of a power plant condenser, in which one of the streams, oh, gosh darn it, I didn't introduce the idea. Notice here in the simplest sketch for a heat exchanger, do you see that we've got two streams of substances involved? One is kind of shown in this blue pipe, and the other is shown flowing in this gray larger pipe. So that's the basic idea. We have two streams of substances flowing. Okay, back to power plant condenser, actual picture. And what's on one of the substances is steam coming out of a steam turbine at a very low pressure, and we're trying to condense that steam. And the other substance would be something like river water or lake water, some type of cooling fluid that's absorbing energy from the steam in order to be able to condense the steam. Okay, so this is a cross-sectional view of that condenser. So this gives you an idea of, you see up here, this red steam, and then what's going out is be condensed steam or condensate. And on the other side, the other substance in blue is going to be water, some water inlet, and it flows through this piece of equipment inside tubes. It doesn't mix with the steam, and it gets warmer because it's absorbing energy from the steam, and then out it goes back to the river or lake or wherever it came from. All right, so I'm going to talk more about this. This is called a shell and tube heat exchanger here in a second. Here is a heat exchanger where steam is admitted into one of these pipes and air is flowing across the ribbed pipes to be heated up. So steam is heating air. Here's an example of one which is an evaporator. I think I've got a bigger screenshot of this, and so I'll save that at a later time. Same thing here. I think I've got some discussion coming up ahead on this piece of equipment. But recognize they're all examples of heat exchangers, and there's two substances involved. Okay, and so here's a real world example of what we call a shell and tube heat exchanger. And to give you an idea of the physical size, I've drawn in the stick figure. And of course, heat exchangers come in a bunch of different sizes, but in general, you get the idea that it's not some tiny little piece of equipment, nor is it some humongous piece of equipment. So in many cases, a person like this can stand up next to the shell and tube heat exchanger. All right, so we've got two fluids. Notice this blue fluid is coming into a almost like a vessel, and this vessel, though, has got a bunch of tubes inside it, inside a tube sheet, or rolled into a tube sheet, okay, or a manifold, you might call it, okay. And so this blue fluid is coming in, and it's being heated up by a hot fluid. So it comes in here, flows through the inside of tubes, it comes out through this manifold, makes a U-turn, and comes back another set of tubes, and now it's really heated up, and out it goes for some process. So that's one fluid. The other fluid or substance is coming in hot, and it's coming into the what we call the shell side. That's like in the vessel part of the heat exchanger, and it's flowing up and down and up and down across up across these dividers, these dividing plates. And so instead of just flowing in one direction, it sort of goes up and down, like I'm showing with my cursor, so that it really mixes, it exchanges energy with the substance that's flowing through the inside of the tubes. Okay, so some things to observe about modeling this heat exchanger. It's clearly an open system, isn't it? I see with my eyes flow in and out. We're going to consider that this process is operating steady state, steady flow. The heat exchanger is not getting bigger and smaller. The flows are not changing between breakfast time and lunchtime. All four of these flows are the same at all time. Okay, they're not changing. Usually for a heat exchanger, we usually have two inlets and two outlets. So you can see with your eyes, let's see inlets. I've got an inlet here and an inlet here, and I've got an outlet here and an outlet here. And the other thing that's very important that a lot of students, they say, well, I wasn't told this, but so it's important to understand. These two streams, these two flow streams do not mix with each other. They are physically separated by the equipment itself, by those tubes. And the other fluid is contained within the shell. And so remember something from early in this class. On its own, heat only flows from hot to cold. So there's one thing we know for darn sure. The hot fluid is giving up its energy and the cold fluid is increasing its energy. Okay, so some other thermodynamic modeling details that we really need to cover. Okay, let's see, we've got open system. Little jargon. Remember, I call this the tube side going in. Tube side fluid going in, going through those little tubes, coming out through a manifold, making a U-turn, going through more little tubes, and then out it goes. Shell side in, shell side out. Do you see this heat exchanger lifting a weight? No. Do you see any rotating shaft? Is there a shaft drive, anything rotating? No, it's just a shell and a bunch of tubes. It's pipes. Okay, so we can say W dot out is 0. Absolutely. We're going to say that this heat exchanger shell is fully insulated. In other words, it's adiabatic between. So we've got lots of insulation covering this shell. And we're eliminating any heat transfer from the shell out to the surroundings. From the shell surface to the surroundings, that's 0. There's no heat transfer there because of insulation that we've wrapped this piece of equipment with. So that's important. Q dot into the surroundings is 0. So why do we call it a heat exchanger in the first place then? Well, I think it's sort of a common sense and it's jargon. So we know as engineers that the hot fluid is exchanging energy with the cold fluid, and the mechanism by which it is heat transfer from hot to cold. So that's why we call it a heat exchanger, because the mechanism is heat transfer from a hot surface to a cold surface within the heat exchanger. Another detail that's not brought up much in the textbook at all, but they just ask you to believe it, is that the tube side inlet and outlet pressure is about the same. In other words, on the tube side, the pressure loss of what I just scoped out into out is negligible. No pressure loss, no pressure drop on the tube side. Similarly, it doesn't matter, these don't have to be equal pressures, tube and shell, but the shell side pressure in is going to be about the same as the shell side pressure out. There's negligible pressure loss in our thermodynamic model of this heat exchanger. So my third note, constant pressure process, little to no pressure drop in tubes or shell. That's going to be important in your problem solving, especially coming up in a later chapter. Okay. Constant pressure process, what did we just cover? open system, steady state, steady flow, 2 inlets and 2 outlets. W dot is 0. Q dot from the shell to the surroundings is 0. And also both of these flows are constant pressure processes. That's some important stuff. Now, what is your sketch going to look like? So the other thing is, I'm going to show you 2 methods by which to sketch this situation. And the way you choose, the method you choose depends on what you're trying to find. So let's get started on this. Here, method number 1 is the simplest way. This is called a 2-pipe counterflow sketch. Do you see why? So I've got 2 inlets, 2 outlets. It's an open system, steady state, steady flow. Do you see why it's called counterflow? Let's look at the hot fluid. It's going through 1 tube. Now I've colored it blue, but imagine that it's hot. All right, 1 to 2, that's hot fluid. 3 to 4, that's your cold fluid. And it's coming in at 3, leaving at 4. And do you see how it's going counter? It's going counter to the hot fluid. That's why we call it counterflow. So this is classic. This is a classic way to sketch a 2-pipe. See, it's made up of 2 pipes, a little pipe in blue and a big pipe in gray, also known as the shell. But just think of it as a big pipe. Okay, got it. That's your sketch. That's your basic sketch. But you're going to say, let's flesh this out for more thermodynamic modeling. Oh, I got to take a little side trip. Here's my basic sketch I just showed you. I want you to imagine in your head, so this has got some value. It's not just getting off track. In your ME 3304 class, so this is a little bit of a preview for what you're going to be covering in ME 3304, is a temperature map. I call this a temperature map. And what you're doing is you're plotting temperature on the y-axis against heat exchanger position on the x or position axis. So let's look at the hot fluid first. Do you see that in your imagination, you're going 1 to 2. And so down here in terms of x and temperature, you're going from 1 to 2. The hot fluid's getting colder, isn't it? All right, got it. So I'm just going to plot an arrow that's going down. How about 3 to 4? The cold is coming in at cold, and it's getting heated up, 3 to 4, okay? So that's your basic heat exchanger map. But what I want to put out is, notice how within the heat exchanger, the distance between these 2 lines represents delta T, doesn't it? And so in ME 3304, this gives you the ability as an engineer to kind of visualize delta T to satisfy yourself that, yes, there is heat transfer between the hot fluid and the cold fluid, delta T. That's really important, but I'm getting off track a little bit. So let's go back to your thermodynamics class. Let's draw a full-fledged thermodynamic model sketch for your problem. And here's my dashed line control surface. So if I draw my control surface around this whole sketch, you do see that I've got 2 inlets and 2 outlets. And how about okay, and also showing Q dot in, I'm showing an arrow, but I'm making it equal to 0. And W dot out, I'm showing an arrow, but I'm making it equal to 0. Continuity equation for both sides. How about the hot fluid? Steady state, steady flow. M dot 1 equals M dot 2. That's a statement of continuity. M dot 3 equals M dot 4. There's the cold fluid, continuity. Now, let's write the first law of thermodynamics, steady state, steady flow, 2 inlets, 2 outlets for my control surface I've drawn in dashed line. Okay, here we go. Q dot in minus W dot out. Both of those are 0, so equals 0. Equals the sum of the M dot leaving, H leaving. So I've got M dot 2, H2, and M dot 4, H4. Both of those are positive. Minus the quantity. What's leaving? What's in? Pardon me. I just covered the leaving. Minus quantity of what's coming in. M dot 1, H1, and M dot 3, H3. So I hope you see, without me dragging out sitting the fundamental and scratching out terms, I hope you can get this in your head right off the bat. Okay, that's my hope. Remember this. So you've got the first law, steady state, steady flow, multi-in, multi-out in your head. And so let's simplify. M dot 1 equals M dot 2. Okay, so I'll take that out. Equals H1 minus H2 equals M dot 3 times H3 minus H4. Oh, so you see I flipped some things around. I didn't show all my steps, but this is basically a statement of the first law, isn't it? It's not a formula. It's not something you should write down on a formula sheet at all. You really ought to start with this statement of the first law and then derive this statement right here. So I strongly encourage you to not use this as a formula, because that is a recipe for disaster. But that's the way, if this is the way you draw your sketch, and method number one, drawing a control surface around everything, 2 inlets, 2 outlets, this is the result you're going to get, and you're going to be able to solve for what you're asked to solve for. It might be one of the flow rates. Okay. It might be H4. You might have to solve for H4 and then ultimately find T4. But you get the idea. This is a study in finding the unknown that you're asked to find. Now I want to show you method 2, and there's a reason I'm going to show you method 2, and that is that on an online call last semester, I was working with a student who had a homework problem. He was working through it, and he was working sort of through method 1. And I said, let me show you how to determine the heat transfer between the hot and the cold, because do you see, if you use method 1, you really have no idea how much heat is being transferred from the hot to the cold. He said, yeah, okay, I see that. Show me how you do that. And so I worked with him to come up with method 2. I didn't make this up. This is common engineering approach, by the way. So let me show you method 2, another way to solve the same problem. Here's our problem at hand, a basic 2 inlet, 2 outlet heat exchanger. What I want to propose is to bust the problem up into 2 separate little problems that are easier to solve. Okay. So the first thing we're going to do is we're going to come over here to the left, and we're going to write the first law for just this blue pipe, just the blue pipe. So I'm going to split out. I'm going to have a different sketch. Okay. And my sketch is going to be a plain old pipe going from 1 to 2. I'm going to call it hot in at state 1, and there's state 2. And I'm going to draw a control surface around that one pipe. I got 1 inlet, 1 outlet. Okay. W dot out, not lifting a weight, no shaft coming out. W dot out, 0. Q dot in, okay, from 1 to 2. Well, that's less than 0 for this situation here, because this is my hot fluid. I've got heat flowing out of my hot fluid, don't I? So I'm going to recognize it's less than 0. I should have started with the cold to make it clearer. Let's split out our cold fluid. It's a pipe, okay? This time, gray pipe. I've got 3 coming in and 4 coming out. 1 inlet, 1 outlet, steady state, steady flow. W dot out is 0. Q dot in is a positive number. I'm heating up my cold fluid. I'm going to expect a positive number. So when I was working with the student online, I said, now, do you observe that these 2 heat transfers, they've got to match each other exactly, except one's negative and one's positive. So I guess I should have said the absolute value of each of them equals 0, but you get the idea. Numerically, this value exactly equals the negative of that value. That's the important thing. And so I showed that student, I said, hey, so this is a way to get a number to really fully understand how much heat you're transferring from hot to cold. He said, yeah, okay, I got it. It turns out that he had a test problem. It was test 2, and he had a test problem where this method 2 really came in handy. So the question was, how much heat is transferred from 1 to 2? He nailed it. And very few students in his class got it, but he got it. And so that made me feel real good. That made me feel very happy that I was able to sort of show that student how to do two methods of analyzing a heat exchanger. Oh, and so that if we write the first law, I took it one step further. So I wrote the first law for the sketch I just showed, okay, here. And then I wrote the first law for the sketch, the cold fluid here, just wrote it, okay. And so therefore, when we made the observation that Qn from 1 to 2, negative of that equals Q dot n from 3 to 4, you get exactly the same result that I had from method 1. So do recognize that. You get exactly the same result. You can show that these two are identical methods for solving the same heat transfer problem. Let me show you some screenshots quickly of other heat exchangers. The same fundamentals apply. So in other words, your sketch for this crazy looking piece of equipment, which is the evaporator section of a home air conditioning system, you would draw the sketch exactly the same way, but basically here we have warm air flowing in a duct from your living space. That this would be a summer cooling situation. It's warm air coming in to be cooled, and so state 2, this is cool air going back to your room. And what are we doing? We've got really, really cold refrigerant coming in at 3 into these cooling coil tubes, finned cooling coil tubes, and coming out at 4 hotter or warmer. And so you get the idea then that we're exchanging heat from air into refrigerant. This is an example of an air to water heat exchanger. It's part of a power plant that recovers energy from hot exhaust gas. And so we've got hot exhaust gas from a boiler coming in here, extraordinarily hot. It's being cooled down. So this is going to the exhaust stack. And the way we're cooling it down is we're recovering energy from the flue gas by taking in high pressure boiler feed water from a condenser, and we're heating it up with that exhaust gas, and then we're sending it on to the steam generator or boiler for additional heating to turn it into steam. So this is a water to air or air to water heat exchanger. Okay, here is a steam to air heat exchanger. So we've got steam coming into this pipe, okay? It is heating up, it's condensing. It's condensing. Why is it condensing? Because we've got cold air coming in from outside. This is the wintertime situation. Cold air coming from the outside, it's being heated up by the steam, and nice warm air is coming into a working space or manufacturing space. And so this steam is condensing and being returned back to a condensate handling location. And so this is not considered a condenser. It's called a steam air heater, even though the steam turns out to be condensing. Let's say you might want to look at some additional videos. If you go to my thermodynamics fundamentals playlist, I've got a 40-minute video giving you some background on heat exchangers and working out some real-world problems. Further, effectiveness of heat exchangers has to do with material you learn in chapters 5 and 6. So what's the recap of this heat exchanger situation? The purpose of a heat exchanger is to transfer energy from a hot fluid to a cold fluid. Those fluids don't mix. Okay. I just showed you 2 identical methods for sketching and solving a thermo problem related to heat exchangers. Recognize that the method number 2 that I showed you is good for finding the actual amount of heat transfer rate going from the hot fluid into the cold fluid, where method 1 did not include that in the computation. So I hope that helps. I hope that helps you understand. Hope that helps you understand more about heat exchangers and fills in some blanks where the textbook may just drop the word heat exchanger and not give you a good full explanation of what the purpose of a heat exchanger really is.